turns of the secondary side, and S is the reluctance. By putting the values, we get L2 is equal to 9.043 Henry. So here we found the self inductance of each coils, coil 1 and coil 2. Now we have to find the mutual inductance between two coils. So the formula we derived, when we derived coefficient of coupling, we derived this formula M is equal to K into under root L1 L2. Now taking coefficient of coupling K is equal to 1, we can find M is equal to under root L1 into L2. We find both the values of L1 and L2. So by simply putting the values of L1 and L2, we find the mutual inductance M. So the mutual inductance M is equal to 0.452 Henry. Now we have to find the induced EMF. So the induced EMF in coil 2, when the current in coil 1 changes from 0 to 10 milliampere in 0.01 second. So here we have formula E2 is equal to M di1 by dt. When we discussed about the coefficient of mutual inductance, we derived this formula E2 is equal to M di1 by dt, where M is the mutual inductance, di1 is the change in current, and dt is the time taken by the current. So here by putting these values, we can find E2 is equal to 0.452 volt. Now we are coming to magnetic hysteresis. What is magnetic hysteresis? So first of all, we have to see hysteresis loss. What is hysteresis loss? So when the iron piece is there or any ferromagnetic material is there, the dipoles will be randomly. They will align randomly. Here we can see that the materials before applying the MMF, the polarity of the molecules or structure are in random. So the molecules are in random if we are not applying the MMF. And after giving the supply or after applying the MMF, all the molecules will be set in one direction, or we can say all the molecules will be aligned in one direction. So the molecules will consume some energy to align themselves, and this energy is not utilized. So this energy is lost. So basically hysteresis loss is energy loss, and this loss is taken by the molecules to align themselves when the MMF is given. Here we have magnetic hysteresis loop, which is also known as BH curve, where B is the magnetic density and H is the magnetic intensity. We can see here what is magnetic hysteresis loop. Here we have an unmagnetized iron piece. A coil is wound over this unmagnetized iron piece. Rheostat is given. Supply is given and a switch is given. So here when we will close the switch, the current I will flow through the circuit, and if I will increase, then H will increase, because we know that H is equal to Ni by L. So if the current in the circuit is increasing, then the H, which is magnetic intensity, will also increase. Now if the magnetic intensity is increasing, we know that B is directly proportional to H. It means that the magnetic density is directly proportional to the magnetic intensity H. So here H is increasing, so B will also increase. If H increases, B also increases. So we can make a hysteresis loop here. B is given on y axis and H is given on x axis. Okay, now if we will increase the current, the H will increase and accordingly the B will also increase. At this point the B will get its saturation value or maximum value, and after that B will not increase. Then we will decrease the current by simply increasing the rheostat or simply increasing the resistance. So here at this point we will get the magnetic intensity 0, but the magnetic density will have some value. So this portion is known as residual magnetism. By decreasing the current, we can decrease the intensity at 0, but the magnetic density will have some value. It means that the magnetized ion will not be fully unmagnetized at this point. After that we have to unmagnetize this ion piece. So we will further increase the value of H in opposite direction. So how can we increase the value of H in opposite direction? So we can easily change the battery connections so that the current direction will change and accordingly the direction of H will change. So here in negative direction we are increasing H. So at this point we can say at point 3 we are getting the value of magnetic density as 0. It means that the ion bar is fully demagnetized here. So the force taken to unmagnetize the ion bar, which is we can say in portion 2 to 3, that force is known as coercive force. And if we will further increase the value of H, then it will get the saturation point on the negative direction. At this point again we are getting residual magnetism or retentivity, and it completes the hysteresis loop. So this is the hysteresis loop. Here we can see the relationship between H and B is non-linear. As unmagnetized core, both B and H will be at 0 at point 0 on the magnetization curve. If the magnetization current I is increased in a positive direction to some value, the magnetic field strength H will also increases linearly with I, and the flux density B will also increase as shown by the curve from point 0 to point A here. After that, now if the magnetizing current in the coil is reduced to 0, the magnetic field around the core reduces to 0, but the magnetic flux does not reach 0 due to the residual magnetism present within the core, and this is shown on the curve. Here we can say that the residual magnetism is from 0 to B, and then to reduce the flux density at point B to 0, we need to reverse the current flowing through the coil. The magnetizing force which must be applied to null the residual flux density is called the coercive force. This coercive force reverses the magnetic field, rearranging the molecular magnets until the core becomes unmagnetized at point C. So here at point C, the core is becoming fully unmagnetized. An increase in the reverse current causes the core to be magnetized in the opposite direction, and increasing this magnetization current will cause the core to reach saturation but in the opposite direction, point D on the core, which is symmetrical to point B. So here at point B we get saturation in one direction, and point D we get saturation in another direction. If the magnetizing current is reduced 0 again, the residual magnetism present in the core will be equal to the previous value but in the reverse direction or reverse point. Again reversing the magnetizing current flowing through the coil, this time into a positive direction, will cause the magnetic flux to reach 0, point F on the curve, and as before increasing the magnetization current further in positive direction will cause the core to reach saturation at point A. Then the BH curve follows the path A, B, C, D, E, F and A, as the magnetizing current flowing through the coil alternates between a positive and negative value, such as the cycle of an AC voltage. So this path is called magnetic hysteresis loop. Here we have magnetization or BH curve for different kind of metals. For steel we can see the magnetization curve, for iron we can see the magnetization curve, and for air we can see the magnetization curve. Here is hysteresis loss, we discussed it. Here we have hysteresis loss for different materials. See, different materials or different magnetic materials have different hysteresis loss and they are having different applications. Soft magnetic materials like silicon or iron, which are used to make the core of transformer and other electrical machines, they possess hysteresis loop which is very tall and narrow. But hard magnetic material will possess a very big hysteresis loop. So the area of the hysteresis loop, we can compare low hysteresis loss and high hysteresis loss. Here two figures are there. The first figure is for soft magnetic materials which are having tall and narrow hysteresis loop, and the second figure is for hard magnetic materials, and the area is also increases in hard magnetic materials. If the magnetic field applied to a magnetic material is increased and then decreased back to its normal value, the magnetic field inside the material does not return to its original value. Here we can see the factors which affects the hysteresis loss. The first factor is frequency. If the frequency will be changing, the hysteresis loss will be changing according to the frequency. If the volume of the material increases, then the hysteresis loss will increase. Then the area also affect the hysteresis loss. So if the area enclosed by the hysteresis loop will be more, then the hysteresis loss will be more. Here we have eddy current loss. Because of time variation of flux flowing through the magnetic material, current is induced in the magnetic material following Faraday's law. So this current is known as eddy current. Now we will discuss about the energy stored in a magnetic field. In previous lectures we discussed about the energy stored in capacitor, but here we will discuss about the energy stored in magnetic field, or we can say the energy stored in inductor. So we consider a coil wound over an iron bar and a current is passed through the coil. So the current through the coil will increase gradually due to the inductance factor. If the current in the circuit increases from 0 to a finite value of I ampere in a finite time dt, then the induced EMF is given by E is equal to L di by dt. The energy consumed in time dt is dW is equal to E into I into dt, where the value of E is put as L di by dt. So we can finally get the energy consumed in time dt as dW is equal to Li into di, and the work done to enable the final current I to flow will be L into I square by 2. So finally we get the energy stored in magnetic field is W is equal to half Li square, and the unit of this energy is joule. Again we have example of this energy stored. Here we are given air cooled solenoid 75 cm in length and 6 cm in diameters. It has 2500 turns uniformly wound over it. So we have to find the inductance and energy stored in the magnetic field when 3 ampere of current is flowing in the solenoid. It means that we are giving 3 ampere current. The length is given as 75 centimeter and the diameter is given as 6 centimeter. So the cross sectional of the area will be pi by 4 into d square. Here d is 0.06 meter. So we get cross sectional area 2.826 mm square. L is equal to n phi by I, but phi, which is flux, is equal to the density into the area. But the density is equal to mu 0 into h, because mu r is 1. So we get phi is equal to mu 0 into h into A. But the h is magnetic intensity, which is Ni by L. So putting all the values, we get the value of phi as 3.55 into 10 raised to minus 5 Weber. Then we have to find the inductance L. So the formula of L is n phi by I. By putting the value of n as 2500, the value of phi is putting and the value of I is given. So finally we get the L as 29.58 mH. So finally the energy stored in the magnetic field will be given by half Li square as we derived earlier. So by putting the value of L and by putting the value of I, we finally get the energy stored in the magnetic field as 0.133 joule. So this was all from the presentation. I am thankful to Gujarat Technological University for giving me this chance. Hope you understood all the fundas. Thank you.